Dear friends, we are going to learn now. In age triggered flip flop, there are another flip flop which is developed, which is known as a JK flip flop. So, age triggered flip flop with a positive RS age triggered flip flop and negative RS age triggered flip flop, and similarly D type of positive and negative age type age triggered flip flop we have studied. Now, there is a limitation in clock age triggered RS flip flop, and that limitation is regarding its forbidden condition. In a age triggered RS flip flop, you cannot apply R is equal to S is equal to 1. Otherwise, both the output Q and Q bar will be the same. This is the drawback in clock RS flip flop. So we have to be careful that this state R is equal to S is equal to 1, which is a forbidden condition, should not be imposed. And we have to take care that it should not be imposed. Otherwise, the output, both the outputs are going to be at the same level. To avoid these conditions and moreover to add these conditions at some advantage in counting the number of positive edge or negative edge, that is done in JK flip-flop. So JK flip-flop is a modified version of edge triggered RS flip-flop where three input AND gates are utilized. So we are going to study this one, and using this counting the number of positive edge or negative edge, we can count the number of clock pulses passing in certain period of time, and hence we can measure the time and we can synchronize the total digital system using this counter. So now the next topic 8.5 is age triggered JK flip flops. Setting R is equal to S is equal to 1 with age triggered RS flip flop forces both Q and Q bar to be the same logic level. This is an illegal condition and it is not possible to predict the final state of the Q. The JK flip flop accounts for this illegal input and is therefore a more versatile circuit. Among other things, flip flops can be used to build counters. Counters can be used to count the number of positive transitions or negative transitions of the clock pulses. For this purpose, counting the JK flip-flop is ideal element to use. So there are many commercially available age-triggered JK flip-flop. Let us see how they function. So in a JK flip-flop also, we can have a positive age-triggered JK flip-flop as well as negative age-triggered JK flip-flop. In figure 8.24, the pulse forming box changes the clock into series of positive pulses, and thus this circuit will be sensitive to the positive transition of the clock. That means in a clock RS flip-flop, that clock is replaced by or clock is going to be given to the positive pulse forming circuit, and output of the positive pulse forming circuit is nothing but series of positive pulses, and this series of positive pulses will be utilized as a clock for a RS flip-flop. And then after there is a crossover connections. That means Q is connected to one of the input of lower AND gate and Q bar is connected to one of the input of upper AND gate. That way cross connection of output to the input is done, and that way the age triggered RS flip-flop is converted into age triggered JK flip-flop. In figure 8.24, the pulse forming box changes the clock into series of positive pulses, and thus this circuit will be sensitive to the positive transition of the clock. The basic circuit is identical to the previous positive age triggered RS flip-flop with two important additions. The Q output is connected back to the input of lower AND gate, and the Q bar output is connected back to the input of upper AND gate. This way, the RS flip-flop is modified. This cross-coupling from outputs to the inputs changes the RS flip-flop into the JK flip-flop. The previous S input is now labeled as a J and previous R input is now labeled as a K inputs. Here is how it works. We will see through the circuit also. When J is equal to J and K are both low, that means both are going to be 0, both the AND gates are disabled and therefore clock pulses have no effect. Thus, the first possibility is the initial entry in the truth table. As shown, when J and K are both zeros, Q retains its last value. When J is low and K is high, the upper gate is disabled. So there is no way to set the flip-flop. The only possibility is reset the flip-flop. When Q is high, the lower gate passes a reset pulse as soon as the next positive clock age arrives. This forces Q to become slow, the second entry in the truth table. Therefore, J is equal to 0 and K is equal to 1 means that next positive transition of the clock reset the flip-flop unless Q is already reset. See this logic circuit of JK flip-flops. 8.24a is a one way to implement a JK flip-flop. This is your normal basic RS flip-flop symbol. ASR, Q and Q bar is there. This box. Then there are 3 input AND gates are going to be utilized. Common input of both this AND gate, one of the common input of both the AND gates are connected to the clock through the positive pulse forming circuits, which is shown by this triangle. That means clock pulse is given to the positive pulse forming circuit and series of positive pulses are going to be generated, that is given as a clock input to this flip-flops, and that way it will work as a H triggered flip-flops. What are the changes made here? Here the S input was labeled as a J and R input is labeled as a K here. So S and R input are interchanged by its name nomenclature by J and K. And the third things, Q, output Q, true output, is connected crossover to the lower AND gate, one of the input, and Q bar is connected to one of the input of upper AND gate. This way, the JK flip-flop was prepared. How it works? So, when the first condition in the truth table, that is J is equal to 0, K is equal to 0, and there is a positive transition will take place. What will happen? You can see in the output Qn, it remains into the last state, no change. That means Qn plus 1 is equal to Qn. Why? J is equal to 0, K is equal to 0. Output of both the AND gates are going to be 0. That means S is equal to 0 and R is equal to 0 for basic RS flip-flop, which is a no change conditions. That means output Q retains its last value. So even if there is a clock pulse is going to be there, but one of the input of the AND gate is going to be 0, output of this AND gate remains to be 0. That's why J is equal to 0, K is equal to 0 is called a no change condition, because it will not activate the flip-flop to make some action and it will retain its last value. That is the first condition in the truth table. Now we can see the second condition in the truth table. J is equal to 0, K is equal to 1. Output becomes 0. J is equal to 0 and K is equal to 1. Again, J is equal to 0, so output of the upper gate is going to be still remains to be 0. That means S input is going to be 0 only. K input is 1. And when the S input is going to be 0, there cannot be possibility that we can set the flip-flops. We have the two possibility normally. We can set the flip-flop or we can reset the flip-flop. But as S is equal to 0, we can not set the flip-flop. Only other possibility is left, that the flip-flop can be reset. If it is not reset, So if it is not reset, that means output Q is equal to 1. So the flip-flop output position is going to be 1. That means Q is going to be 1 and Q bar is going to be 0. So Q is going to be 1. That means second input of the lower AND gate is also going to be 1. This K is equal to 1. Second input of the AND gate is also going to be 1. And when the positive edge is going to be occur, all the three inputs becomes high, or you can say that the flip-flop becomes enable and R becomes 1, S is equal to 0, which can reset the flip-flop. So Q is changed from 1 to 0. And hence the Q is going to be flip-flop is going to be reset. So that is the second entry in the truth table. Similarly, there is a third entry in the truth table. J is equal to 1, K is equal to 0. So if J is equal to 1 and K is equal to 0, you can apply the same logic. As K is equal to 0, output of the lower NOR gate is going to be 0. Output of the lower NOR gate is going to be 0. That means R is going to be 0. R gets the input is equal to 0. So you cannot reset the flip-flop. That means only other possibilities left. You can set the flip-flop only if it is not set. If it is not set, that means output is flip-flop is already in reset conditions. Then you can set the flip-flop. That means output Q is going to be 0 and Q bar is going to be 1. Q is going to be 0 and Q bar is going to be 1. So Q bar is going to be 1. This is coming as an input to the upper AND gate. So one of the input of the upper AND gate, Q bar is going to be 1, J is going to be 1. So when the negative positive edge of the clock pulse occur, then all the three inputs becomes 1 and output of this AND gate is going to be 1. So S becomes 1 and R becomes 0, which can set the flip-flop. That means Qn plus 1 is going to be 1. So that is the third entry in the truth table. That way you can set the flip-flop. Now the last entry in the truth table. J is equal to 1, K is equal to 1. J is equal to 1 and K is equal to 1. Both the possibilities open now. The flip-flop can be set also and flip-flop can be reset also. It depends upon the output position or output condition or output state of the flip-flop. If the flip-flop is already in the set conditions, that means Q is equal to 1. That means lower gate becomes all the three inputs 1 when the next positive edge of the clock pulse occur. And that way the flip-flop can be reset. That means output can change from 1 to 0, and that way the flip-flop can be reset. If flip-flop is already reset, Q is going to be 0 and Q bar is going to be 1. That means Q bar is one of the input of the upper AND gate. So this input is going to be 1, J input is also 1, and when the next positive edge of the clock pulse occur, all the three inputs becomes 1. So S becomes 1, R is going to be 0, which is a set conditions for the flip-flop, and the flip-flop is going to be set. So Q will change from 0 to 1. So in any case, the output of the flip-flop is going to be complement to its previous value. So if the previous value is going to be 0, then positive edge of the clock pulse will complement it or toggle it, and output is going to be Qn plus 1. Qn plus 1 is equal to Qn bar. That means it is complemented. If it is 0, it becomes 1. If it is 1, it becomes 0. If it is set, it can be reset, and if it is reset, it can be set. So output is complemented with every positive edge of the clock pulse. This is the main characteristic of JK flip-flop. So that we can study here. Third conditions, when J is high and K is low, the lower gate is disabled. So it's impossible to reset the flip-flop. But you can set the flip-flop as follows. When Q is going to be 0 and Q bar is going to be high, therefore the upper gate passes a set pulse on next positive clock edge. This drives Q into the high state. The third entry in the truth table, that means you can set the flip-flop. As you can see that J is equal to 1, K is equal to 0, means that next positive transition of the clock set the flip-flop unless Q is already set or high. Now the fourth condition is explained here. When J and K are both high. Notice that this is forbidden state with the RS flip-flop. It's possible to set or reset the flip-flop. That means if it is set, we can reset it. If it is reset, we can set it. It's possible to set or reset the flip-flop. If Q is high, the lower gate passes a reset pulse on the next positive transition. On the other hand, when Q is low, the upper gate passes a set pulse on the next positive transition. Either way, Q changes to the complement of the last state. See the truth table. Therefore, J is equal to 1 and K is equal to 1 means the flip-flop will toggle. Switches to the complement or output state. Switch to the opposite state on the next positive clock transition. Now, very important things. The propagation delay time prevents the JK flip-flop from racing, toggling more than once during the same positive clock age. So, duration of the positive clock age is very low. Even though if the propagation delay time, what is the propagation delay time? Once the input hit the flip-flop, that means output of the flip-flop is going to be resulted after certain minimum time. It is not going to be resulted immediately, and hence this minimum amount of time it takes number of clock pulses. In figure 8.24, the output changes after the positive transition of the clock. By then, new Q and Q bar values are too late to coincide with the positive transitions driving the AND gates. For instance, if the TP is equal to 20 nanoseconds, hello. For instance, if the TP is equal to, that its propagation delay time is of 20 nanoseconds, the output changes approximately 20 nanoseconds after the leading edge of the clock pulse. If the positive transitions are narrower than 20 nanoseconds, the returning Q and Q bar values are too late to coincide to cause a false triggering. That means new value of Q and Q bar at the input of the AND gates is too late. So that already positive transition is gone and it will wait for the next positive transition of the clock pulse. Figure 8.25a shows the symbol for the JK flip-flop of any design. When you see this on a schematic diagram, remember that on the next positive transition of the clock pulse, what happens? There are different state is given. When the next positive transition of the clock will there, J and K are low, no changes in the output state. That means it retains the last value. J is low and K is high. Q is going to be reset and Q becomes 0. This is called reset conditions. Third condition, J is high and K is low. Q is going to be set and Q takes the value of 1. And the fourth condition, when J and K are both high, Q toggles to opposite state. You can include OR gates in the design to accommodate preset and clear as was done in a D flip-flop. Figure 8.25b gives the symbol for JK flip-flop with preset and clear. Notice that it is negative edge triggered and required a low preset to set it or low clear to reset it. These are a various symbol for JK flip-flops. JK flip-flop can be positive edge triggered also as well as negative edge triggered is also. Because sometimes it is negative edge triggered, JK flip-flop is more suited than positive edge triggered. In that case, what happens? The positive pulse forming circuit or negative pulse forming circuit is going to be introduced at the input of its clock pulse. And it can be a positive edge triggered JK flip-flop or it can be negative edge triggered JK flip-flop. But if it is negative edge triggered JK flip-flop, there is an inverter inside the IC has to be there. So the AND gate will respond on complemented negative edge of the clock pulses. So here there are symbols. You have to understand these symbols. There are 3 inputs and 2 outputs. That is the basic symbol of edge triggered JK flip-flop. Now in this one, clock, see how it is mentioned here with a line and triangle inside, small triangle inside. This is shown dynamic indicator. And this indicates that with the positive edge of the clock pulse, the flip-flop is activated or flip-flop will respond to the input conditions of J and K. It can be no change conditions, it can be set conditions, it can be reset conditions, or it can be toggle mode conditions. Any conditions, it is going to be responding on positive edge of the clock pulse. Second one is shown with the negative edge triggered JK flip-flop. Again, the inputs are J, K, and clock inputs is shown with the bubble and small triangle. Dynamic indicator with the bubble. What this bubble indicates? That it is negative edge triggered flip-flop. So what it means? On a negative edge of the clock pulse or trailing edge of the clock pulse or when the clock pulse makes a transition from high to low, this flip-flop are responding on its J and K values. Depending upon J and K values, flip-flop can be set or reset or toggle or no change conditions. So this is a second type of flip-flop, negative edge triggered JK flip-flop. In this flip-flop, you can see there are 2 other inputs is also there. One input is a preset input, other input is a clear input. They are shown with the bubble. What is the indication of the bubble? This indicates that preset and clear, which are asynchronous control, which can directly control the flip-flop without clock pulse. Even if the clock pulse is not occur or it is independent of the clock pulse, when they are going to be low, they are active low here. Bubble indicates that they are active low. So whichever input is made low, accordingly the flip-flop is going to be reset. If the preset input is going to be low, then the flip-flop is going to be preset. That means Q takes the value of 1. And when the clear input is going to be low, then flip-flop is going to be clear or flip-flop is going to be reset and that Q is going to be 0 and Q bar is going to be 1. So that way, these 2 inputs which will activate the flip-flop independent of the clock, hence it is called asynchronous control. They are direct controlling the flip-flops. J and K is a synchronous control like D control. So they will be waiting for the clock pulse to occur. So when the clock pulse occurs, according to the J and K, the flip-flop is responding. So J and K is clock dependent or edge dependent flip-flop. It is there. That's why it is called synchronous inputs. There are certain other ICs also available in the market. 74LS73A, which is having a negative edge triggered JK flip-flop, but it is also having a clear input active low. Figure 8.25C is another commercially available JK flip-flop. It has negative edge triggered and require a low clear to reset it. The output Q reacts immediately to the preset and clear signal. Both preset and clear are asynchronous and they override all other input signals. Example. Now it is called toggle mode conditions or T flip-flop. T flip-flop can be derived from JK flip-flop. So what is the requirement of the T flip-flop or toggle mode conditions, toggle mode flip-flops? Popularly known as a T flip-flop, has following input-output relations. When input T is equal to 0, the output Q does not change state. So when T is equal to 0, that means there is only one input and that is a T input and that is going to be 0. Q does not change the state, it retains its last value. But T is going to be 1, the output Q is going to be toggles its value. So our problem is to derive the T flip-flop from JK flip-flop. How it can be derived? If J and K, both the inputs are sorted and they are labeled as a T inputs, then it converts JK flip-flop into toggle mode condition or toggle mode flip-flop. From figure 8.24b, we find that input J is equal to K is equal to 0. The output Qn plus 1 is equal to Qn. The output does not change its state, it retains its last value. And for J is equal to K is equal to 1, the output Qn plus 1 is equal to Qn bar if the output is going to be toggles. Thus, if we tie J and K inputs to of JK flip-flop together and makes a common input T is equal to J is equal to K, the resulting circuit will be used as a T flip-flop. Now, there are certain questions related with this topic. What is the primary difference between a JK and RS flip-flop? What is the primary difference? In RS flip-flop, you cannot utilize 1-1 condition. R is equal to S equal to 1, that is a forbidden conditions. The output is unpredictable. And JK flip-flop, you can utilize these conditions to count the number of clock edge, because on every positive edge or negative edge, the flip-flop is going to be toggle. So it will work as a counter. How could you change an edge-triggered RS flip-flop into edge-triggered JK flip-flop? By using cross connections of outputs to the inputs. Q is connected to one of the inputs of the lower AND gate and Q bar is crossover and connected to the upper AND gate, one of the inputs. And that way, the clock edge-triggered RS flip-flop is converted into edge-triggered JK flip-flops. Now we'll discuss about the flip-flop timing. Diode and transistor cannot switch state immediately. It always takes a small amount of time to turn a diode on or off. Likewise, it takes a time for a transistor to switch from saturation to cutoff and vice versa. So you know that diode, when it is forward bias, it starts conducting. That means from N-type material to the P-type material, or another way you can say that the electrons can flow from N-type material to the P-type material and the conventional current is established from P-type material to the N-type material. And this current is going to be set up after certain minimum cut-in voltage. So the diode takes time to change from on to off or off to on. Similarly, transistor also, you have studied the characteristic of the transistor and DC load line of the transistor. So we are utilizing two distinct points of the load lines, that is cutoff and saturation. So when the Q point is at the cutoff, the transistor is off, and when the transistor is on, the Q point will be at saturation. So even similar way, when the transistor is from on to off, there is extra carriers, the base, in the base current has to be established and that will create a collector current. So it takes a minimum amount of time for transistor and diode to switch on or switch off. So diode and transistors cannot switch state immediately. It always takes a small amount of time to turn a diode on or off. Likewise, it takes time for a transistor to switch from saturation to cutoff and vice versa. For bipolar diodes and transistors, the switching time is in the nanoseconds regions. Switching time is the main cause of propagation delay time, and that is designated as a TP. This represents the amount of time it takes for an output of a gate or a flip-flop to change the state after the input have been change. So if there is a set condition is there and you give the reset conditions. So as soon as you give the one reset conditions, the flip-flop is not going to be reset. It will take the time to change from set conditions to reset condition, or Q will be established to 0 after certain minimum amount of time. This minimum amount of time is known as the propagation delay time. This represents the amount of time it takes for the output of a gate or a flip-flop to change the state after the input have been changed. For instance, if the data sheet of the H-triggered D flip-flop lists that Tp is equal to 10 nanoseconds, it takes at least 10 nanoseconds for Q to change the state after D has been sampled by the clock edge. This propagation delay time has been used to construct a pulse forming circuit used with the H-triggered flip-flop that we have seen in a last semester, that positive pulse forming circuit and negative pulse forming circuit was prepared using this propagation delay time of NAND gate and AND gate, etc. When the flip-flop are used to construct a counters, the propagation delay time is often small enough to be ignored. So when we are utilizing this JK flip-flop to work as a counter, the clock period is larger, very larger, and hence for counting the number of clock pulses, we can ignore this propagation delay time. But now the second type of the things is called the T setup time. How it is going to be there? Stray capacitance at the D input or any input of the flip-flop plus other factor makes it necessary for data bit D to be present at the input before the clock edge arrives. So whatever data, either D input is there, S and R input is there, or J and K input is there, that must be present prior to the clock edge arrives. That means either the positive edge of the clock pulse is allowed or negative edge of the clock pulse is to be arrived, data has to be remains present prior to that. So the minimum amount of time prior to the clock edge arrives that has to be present, then only guaranteed operation is possible. This time is called T setup time. Stray capacitance at the D input plus make other factors makes it necessary for data bit D to be present at the input before the clock edge arrives. The setup time T, which is called T setup, is the minimum amount of time that the data bit must be present before the clock edge arrives. For instance, if a D flip-flop has a setup time of 15 nanoseconds, data bit to be stored must 1 or 0 must be present at the D input at least 15 nanoseconds before the clock edge arrives. Otherwise, the manufacturer does not guarantee correct sampling and storing. Furthermore, data bit T has to be held long enough for the internal transistor to switch the state. Only after the transition is assured can we allow data bit to be changed. So even after the positive edge hit the flip-flop, then the action inside the IC start. That means transistor will go from on to off or off to on. And once for that, you have to wait for that data bit has to be there itself. We have to hold that data bit for some minimum amount of time. So this amount of time is called T hold time. Furthermore, data bit D has to be held long enough for the internal transistor to switch the state. Only after the transition is assured can we allow data bit D to change the state. Hold time. T hold is the minimum amount of time that data bit D must be present after the positive transition of the clock. For example, if T setup is 15 nanoseconds and T hold is 5 nanoseconds, data bit has to be at the D input at least 15 nanoseconds before the clock edge arrives and held at least 5 nanoseconds after the positive transition of the clock pulse. Now there is an example related with this one. Typical waveform for setting a 1 in the positive edge triggered flip-flop are shown in figure 8.26. Discuss the timing. We can discuss the timing in this figure. So the lowermost is the timeline. We can take the reference of the clock pulse. This is the positive edge of the clock pulse, which is changing from low to high. At that time, we have designated that is the instant of time t is equal to t2. Before the clock edge hits the flip-flop, there should be a minimum amount of time that data bit has to be present. So this minimum amount of time, which is called t setup time, which is at the intersection of t1. So time t is equal to t1, the data bit has to be present and it has to be held constant there before the clock edge arrives over there. That means if you want to store any data, D can be 0 or 1, whatever we want to store, that can be changed prior to the T1, anything. So that's why it is shown here that 0 is also shown here, 1 is also shown here. But we want to store D is equal to 1. So what happens after the time T1, the D is equal to 1 is made steady unchanging levels, and that has to be set up when the positive edge is going to be occur. So now it will take the value of t, but it will not occur at the same time. So output q is not going to be takes the value of d at the same time, but it will take output of the flip-flop will be changed after certain minimum time, and that minimum time is known as a propagation delay time Tp. So the interval T2 to T3, that is known as the propagation delay time. After that, the flip-flop is going to be set and Q takes the value of 1, which is from D. And now from the positive edge of the clock pulse until certain period, minimum time, it should be data bit has to be present, unchanging and stable. That is called hold time. It has to be hold up to a time t4. Then after you can change the data in ports 0 or 1. The data is already stored and it is going to be retained. The lower line of the figure 8.26 is the timeline with the critical times marked on it. Prior to the T1, data can be a 1 or a 0 or can be changing. This is shown by drawing line for both high and low levels on the D. From time T1 to T2, the data lines D must be held steady. In this case, it should be 1. This is the setup time T setup. Data is shifted into the flip-flop at time T2 but does not appear at Q until the time T3. So time from T2 to T3 is propagation delay time Tp. In order to guaranteed operation, the data line must be held steady from time T2 until time T4. This is the hold time T hold. After T4, D is free to change the state shown by the double lines. Thank you very much, friends.